Theory and Practice of Silviculture, lecture number 6. In my previous lecture, we have studied about the locality factors and covered about the two categories, that is climatic factor and physiographic factor. Let's revise it back. We have factors of locality, or we call it habitat factor or site factor, which is categorized under 4 categories. Number 1 is climatic factor, number 2 is topographic or physiographic factor, number 3 is edaphic factor, and number 4 is your biotic factor. These 4 factors are very important locality factors or a site factor which influences the vegetation. And this 4 factor is very important for a forester to understand for the management of the forest, to create the forest, conserve the forest, and scientific management of the forest. In this lecture, we are going to study about the edaphic factor, number 3. Edaphic factor is defined as the ecological influence of the characteristics of a soil. Edaphic means soil, brought about by its physical and chemical characteristics. Thus, the edaphic factors are related to the soil in which the tree grows and which therefore forms the environment of the root. That is very important. So, this is a parent material, you can see, and how this is very important means what type of parent material is important, what is your soil conditions, how much your soil is able to give the nutrients, what is its cation exchange capacity, what is its water holding capacity, and this is very important for the growth of a tree, because this soil gives the environment of the roots, and roots are very important because they only provide the nutrients, moisture to the trees to grow. Soil is very essential for the growth and development, ultimate what we want to say. So the various factors affecting the development process, the soil property can be categorized into these 3 things we'll do. One is we'll discuss about the physical property of the soil. Second, we'll discuss about the chemical property of the soil. And third, we'll discuss about the biological property of the soil. First is physical, where we'll have soil structure, soil composition, soil profile, depth of the soil, soil temperature, soil moisture. Chemical will include soil acidity, pH, high or low, then cation exchange capacity, soil organic matter. And biological property have soil organism, microorganism, microorganism, and so on. First is the physical property. Now, very simple physical property is related to supply of moisture, nutrients, air, and cause the influence of tree growth. Now, such property of soil related chiefly to texture, structure, and porosity. Let's texture. What texture we have to? Sand, silt, and clay. Everybody knows about clays. How much you can see the size is less than 0.002 mm, and the silt is between 0.002 to 0.02 mm. Coarse is 0.02 and 2 mm. And then gravel is greater than 2 mm. You can see the granular structure. You can see this blocky one, how it looks. This is a platy one. This is prismatic, and then this is structureless, and so on. Now, I told about the sand is very coarse. Then we have silt. Then we have clay. Now, you just have this one small diagram. The proportion of particles of clay, silt, and sand in the soil influences the physical property of what is the physical property, means how much, because air is important here, how the root has to take the air, respiration has to happen in the root, then what is the water holding capacity in there, what is the drainage there. It affects the growth of your forest, growth of your tree. Let's assume this is a sand. You can see sand here. So if you see sand here, you can see when you see the sand here, what will happen here? 90 to 95% sand. Let's take. You can see water holding capacity is very, very less. Water holding capacity is very, very less. Even the nutrient, we can see cation exchange capacity responsible for nutrient uptake is also very less, because we don't have much of the humus here. for those activity to be done. So you see the pore type of vegetation will happen. But as you sand will be having bit of the silt here, and this will increase the water holding capacity, you will have a medium type of moderate growth here. But when we have clay loam here, see the clay, when we have clay loam here, sand is of 20 to 50% and silt is of 50 to 80%. You can see a very good cation exchange capacity, very good water holding capacity, very good aeration. So very luxuriant vegetation you can have. But when we go further and when we have more clay here, and because when we increase in clay and decrease in other silt and that one sand, then what will happen? Your porosity will decrease. And what will happen? Your heavy clay, what will heavy clay? Moisture will be, your air will be less, it will be, water will be more. So you can have, see the condition again moderate and again very poor. So this is what the proportion of particles. So if we see the composition of soil, we should have a this is a general one, there is 25% of air, water is 25%, and then this is 50%. If you see both, mineral is 45%, and then this is from parent material, and then 5% organic matter. This is the soil composition. Soil includes this mineral metal source decomposition from rock, and then organic matter source from what, plant and animal. And then water, partly liquid and vapor, and gases such as carbon dioxide, ammonia and other things are there. This is a composition of soil. So that's why soil structure is very, very important. So as a forester, let's simplify this soil structure. Soil structure is referred to the arrangement of a soil particle such as sand, silt and clay into aggregates. So just we have seen this one, the combination sand, silt and clay into aggregation. In other words, soil structure is the size, shape and arrangement of solids which affects the pore size and this capacity of a transmitting air, water and dissolving substance, the ability to support the root growth. This is very important. So when we see the soil aggregate, you can see this fertilizers are there, you can see soil particle, this one, and we can see organic matter. This is called one soil aggregate. So this soil aggregate, they make a soil structure, where this soil structure, as I told you, need for a vigorous root growth, and that's why this soil structure is responsible for moisture retention, responsible for cation exchange capacity, that is called nutrient supply, and for aeration, for your respiration of root, and that's why the root development is ultimately with a very good structure, very good root development. Good root development means very good vegetation is there. So let's come to soil profile. Everybody knows soil profile. We can have a soil profile of 6 feet. That way soil profile is defined as the vertical section of the earth inside the earth. Normally the top soil is thicker inside the forest. However, it varies from place to place and type. So soil profile is a great significance for the development of the vegetation. It has 5 layers. One is called O horizon, organic one. This is the O horizon, the top organic. This is organic one, O horizon. Then we have A horizon, top soil, this top soil. Then we have horizon sub B1, leached mineral one, zone of accumulation. This is zone of leaching, and this is accumulate. Here is zone of accumulation. Then this is bedrock on the lower one. This slowly what it has, physical weathering, chemical weathering happens. Then we have what, partly weathered rock here, and then weathered fragmentation here. So this is what a soil profile you will have, and this is very important because it depends on the parent material. So what type of parent materials have, we have a soil profile, and soil profile ultimately gives you the vegetation, tree species on that area. On the other hand, we should also know about the pan formation. There are different pan formation. Let me tell you what is pan. Pan is actually compact cemented soil horizon, which is cemented one. Okay, may be affected by iron hydroxide, organic material like silica, calcium, carbonate or other substances. It also referred to a hard pan. Now what is hard pan? This is all, you can see we have lot of minerals are here. So what will happen, this compounds, if we have limited rainfall here, the rain will percolate down, but after that limited rainfall, we have lot of hot area and lot of temperature has increased, which will make evaporations. This evaporation will make these salts on the lower subsurface to come here on the bit top here, and they accumulate here and create a hard pan. Okay, this hard cementing pan is very hard, even roots cannot penetrate. This is called a hard pan. This is a type like conker pan, alluvial soil, lateritic pan in lateritic type of soil, podzolic soil, silicon soil. This different type of pan formation is there. It is just half feet or 1 feet below the soil you will find, and they don't let the root to grow, and this is very difficult for the tree species to survive here. So depth of the soil is, that's why I am telling that depth of the soil is ultimately depend on the soil profile. So depth of the entire soil mass as well as thickness of the various horizons are important for the growth of forest. Now, total amount of how much water is stored, so that is also very important as per the soil profile. So the depth and physical character of the various horizon determines the growth of a tree root. You can see these are the different soil profiles being here. And then let's come to the physical property. Under physical property we have soil moisture. Now soil moisture means moisture available to the trees. So there are three types of moisture. One is called hygroscopic moisture, one is called capillary moisture, one is called gravitational. So hygroscopic moisture, they are bounded very tightly to the soil particle. See, they are bounded very tightly to the soil particle, and it is not available to the plants so to access, to take. So hygroscopic water. Then gravitational water is to the field capacity, you can see saturation, and it is going down to the gravity. What is available is capillary. Capillary water is very much important and is available to the plant because it goes against the gravity and which is available to the plants. So there are three types of water which is moisture, which is hygroscopic, capillary and gravitational. Among that, capillary is very important because as it affects the vegetation principally, because it assists your soil moisture. What it does, it assists in decomposition of rocks, in the formation of humus. It is an important agent for translocation of mineral from the soil to the plant. So these things are very important as a soil moisture, we have to remember. And also soil aeration. Let's come to soil aeration. When we come to soil aeration, that is also important because aeration affects the root growth. Higher carbon dioxide kills the root, and the optimum is only 1%. So we should have a proper aeration so that your carbon dioxide, they escape from the soil. So that's why soil aeration is important. If you have a poor soil aeration, we have a poor growth of trees. Then chemical properties. After physical, let's come to chemical property. The soil is known to be chemical laboratory now in nature, in which soil chemical decomposition reaction taking place is hidden manner. Now what are those chemical property we'll study? We'll study about the pH of a soil or soil acidity, cation exchange capacity, which is important for nutrient uptake, and soil organic matter. If you see the pH, 6 to actually optimum is 5.5 to somewhere 8.5. This is optimum, where you can see the tree growth is growing very nicely. In this pH, we have a very good cation exchange capacity, where nutrients is available to the plants. You can see the nutrients are available to the plants in this pH. But as the pH goes down, your aluminum toxicity, heavy metal toxicity happens here. Deficiency of phosphorus, calcium, then magnesium, all this happens in the acidic soil. And when it is a high pH goes to 12, 13, 14, deficiency of iron, then deficiency of phosphorus, zinc happens in this one. So we should have tree species and identify the forested tree species, that which species could survive if we have high pH, we have more salts, and if we have more to acid, which are the species which can survive. Very less species will be there on the extreme sides. Only the species which are maximum, which we can grow and which can give a better result, will be on the species which are pH which are between 5 to 8. Now, Cation exchange capacity on this chemical property. Let's understand about the cation exchange capacity. CEC, cation exchange capacity, is a kind of a storehouse of organic mineral nutrient which determines the total amount of nutrient available to the plant. The clay mineral is colloidal in nature. Suppose this is a clay mineral, this is a clay mineral, it is a colloidal in nature. Okay, we also call micelles. This is colloidal in nature, means we have negative charge on the inner side, and outer side we have a thin film layer of that one positive charge, attracting positive charge, where it attracts the exchangeable cations here. You can see the cations which has been attracted here. A lot of cations are there. These minerals are very, very important. So this clay micelle, they act as a colloidal nature, behaving the acid radical, attracting the cations on the outer surface. What it does, this is the root of a tree. So root of a tree, they will exchange their cations with, suppose this is their hydrogen ions, this has been exchanged with the mineral, like you can have potassium, calcium is exchanged. So if we have a proportion of clay colloidal properties, then we have a good cation exchange capacity. If you are having only sandy area, so sand has very less cation exchange capacity. That's why the growth in the area of deserts are very, very less, a very, very stunted one. So this is very important as a cation exchange capacity, because it is responsible for the nutrient uptake of the trees. Soil acidity. So acidity of a soil solution is due to excess of hydrogen ion over hydroxyl ion. But if hydroxyl ions are in excess over hydrogen ion, the solution becomes alkaline. Now, acid soils are formed by removal of bases, usually in humid climates. When we see this humid climate, the acid soils are formed by removal of bases. You can see this is the bases. As we can see the blue color here, these are the bases, the hydrogen ions. The pH may be low as 4.0. It may be low as 4.0 here in acid soil. You can find this one in coniferous forest, or you can find in humid climates also. But soils in the tropical moist deciduous forest and evergreen forest are very acidic here. You can find this is the soil solution here, and low pH here and high pH in semi-arid area. In alkaline soils, in arid and semi-arid regions, there is no leaching of bases. Here we don't find any leaching of bases here. This blue color, you can see the leaching of bases is very minimal. Then the upper soil water by means of evaporation, leaving the salts on upper soil. So here very less rainfall and less leaching is here. It makes more salt here. The alkaline reaction will happen here. So these semi-arid areas will have more bases as compared to your humid here. So this humid, you will have more basic cations which has been leached here. Now let's come to the saline soils. There we have three things to under alkaline soil, which is grouped into three. One is called saline soil, alkali soil, and saline and alkali soil. Let's come to saline soil. First, saline soil pH is generally less than 8.5. Saline soil is called white alkali because it gives the observed with whitish efflorescence from the far. That's why it is called white alkali. The salts, these salts are usually chlorides, sulfides, carbonates, and bicarbonates of sodium, calcium, and magnesium. Now, what is the property? Number one property is soluble salt percentage is more than 0.15, and exchangeable sodium percentage is less than 15 in saline soil. The second one is alkali soil. This alkali soil is pH is more than 8.5. This is black in color. Saline soil was white in color. This is black in color just because it dissolves the organic matter, and which imparts is black in color. The property is soluble salt percentage is less than 0.15 and exchangeable sodium percentage is more than 15. And the third category is saline alkaline soil, which is pH is more than 8.5, soluble salt is more than 15, and then exchangeable sodium percentage is more than 15. These are this alkali soil. Now, importance of pH value. Now let's see the importance of this pH value, because optimum is 6 to 8 as per nutrients are available. Generally we can take from 5 to 5.5 to 8.5 also, but the optimum is 6 to 8 pH. Now pH value has a profound influence on the distribution and growth of the forest or trees also, as well as we know that the low pH, what are the trees which are suitable. Some species prefer low pH, some species prefer high pH. Now it has an influence on the availability of nutrients and soil microorganisms. See, this is very important, because 6 to 8 pH is an optimum, because where we have very good decaying of organic matter, where water holding capacity is available, where cation capacity is doing well, where minerals and microbes are acting nicely. So soil acidity is associated with maturity of the soil and climax vegetation also. Now when I say maturity of the soil, it means that I relate it to succession of a forest. When a forest is there, a succession takes place. In the beginning it is a pioneer species when the soil was immature. When the soil was immature, slowly this pioneer species has replaced cereal species has replaced subclimax species, subclimax has replaced after many hundred years to climax species. Climax species has come to the final, you can say, the culminating stage of the plant succession for a given environment, where further no changes happens and that species remains there in a harmony with the environment. We say that maturity of soil happens. So soil acidity is associated with maturity of the soil, of the climax vegetation. So it indicates, soil acidity indicates the immature soil and the mature soil. So we can see the pH. So as I tell, this is a Shorea robusta. We can see Shorea robusta successfully they grows in best in pH from 4.5 to 5.5, and Tectona grandis, they occur from 6.5 to 7.5. This is what the pH also determines the species and the availability of the species, distribution of the species, and liking of the species. Then there is soil organic matter. Soil organic matter is very important, because the soil organic matter is what it does from twigs, barks from the trees, it fall down, and then this is what the decomposition happens. The residuals which makes a humus is partial decomposed, partial leaf litters and other things are there. We can categorize as an acid or sour humus, means decomposition under anaerobic conditions. We call it acid or sour humus. Then we have more, or you can say raw, not mixed very nicely with the mineral soil. Then we have mull or mild humus mixed below mineral soil here. Okay, so this is soil organic matter, very important, because it gives it is the actual blood of the soil. It gives the nutrients to the trees. And the importance, we see the humus, important structure, it improves the structure. When the structure is improved, it improves the water holding capacity. So rate of percolation of the moisture is very important. It makes the sandy soil more cohesive. If you have sandy soil, some trees are growing, it adds some litter, it becomes a humus, then it improves the structure. As it improves the structure, it will improve the colloidal property, that will give you cation exchange capacity. Once the cation exchange capacity increases, the nutrients will be available to the trees. So this is how the importance of humus. Then carbon nitrogen ratio, CN ratio is again very important, because in most forests the major source of nutrient is CN ratio. Now what is CN ratio? See, this is a wood. We'll have what? Would have a lot of cellulose. Means lot of cellulose, CHO, three things will be there, carbon, hydrogen and oxygen. Means lot of carbon is there, isn't it? So generally we say that 50% of the weight of the wood is carbon. If we have 10 kg of wood, then 5 kg is carbon. So CN ratio should be balanced. The carbon to nitrogen ratio, we see carbon to nitrogen ratio should be balanced one. Now let me make you understand. Suppose this is a forest and you see the logs are lying there. If the organic material has less amount of nitrogen, in relation to the carbon. Suppose this is organism, let's take this wood, it is lying down. Here we have carbon more and nitrogen is a bit less. Obviously nitrogen will be less because it is lot of cellulose here. Then what will happen? The microorganism will utilize soil nitrogen for further decomposition. Now to decompose that cellulose, there will be a lot of microorganism in that area, in that particular wood. What will happen? This microorganism, for their own metabolic activity, they need nitrogen. So they will use the nitrogen for their own metabolic activity and they will use it from their soil. More the carbon there, more the microbes will be there. For what? To decompose it. So if carbon is more microbes will be more in that area. Their population will be more to decompose more cellulose there, more carbon there. So what will happen? The microorganism will utilize the nitrogen for further decomposition and their metabolic activities. So what will happen? The soil nitrogen will be immobilized and will be not be available for the plants to take. Now let me make you understand again. The CN ratio of the organic material added to the soil nutrient and the rate of decomposition of the soil organic matter, this results the release of mineralization. If we have a good ratio, balanced ratio, generally balanced ratio is 15:1. When this is a balanced ratio, then it is easy for the microorganism to decompose it and make it mineral available to the plants. On the other hand, if added organic matter contains more nitrogen in proportion to carbon, then the nitrogen released to the soil for decomposition material is good. Now let me make you understand. Here we have more carbon and less nitrogen. Here we have adequate amount, and here we have very good. You can see 10:1. See, if we have a balanced carbon to nitrogen ratio, mineralization will happen. Mineral will be available. And if we have more carbon ratio as compared to nitrogen, then immobilization will happen. Lower CN ratio means greater amount of mineralization. This point. Okay. And 15:1 is assumed to be a good or a high CN ratio. But higher CN ratio, this one, is disadvantage for the plant growth, because see, let's assume the log is lying there. When the logs are lying there, lot of cellulose is there. Cellulose is what? Carbon we have, hydrogen we have, oxygen we have. So more of the cellulose is more carbon. When more carbon is there, then to decompose this one, the population of microbes will increase. So more number of microbes, when they will come to decompose to this entire wood, they need what? More metabolic activity is been required for the microbes to work there. They will require nitrogen for themselves. So available nitrogen in the nearby area, they will eat up. So this is lot of microbes. Increase in microbes will be there to decompose this wood. So what will happen? These microbes, they need nitrogen for their metabolic activity, and nitrogen is already not available because carbon ratio is more to the nitrogen. So it will take the nitrogen from nearby area and then it will go for immobilization instead of mineralization. This is called that high carbon to nitrogen ratio. That's why we should have a balanced ratio 15:1 for our forester to understand to manage the CN ratio. Other one is called silica sesquioxide ratio. Now let's understand the silica sesquioxide ratio. As a result of loss of silica by leaching, sesquioxide get accumulated in the soil profile. It happens in the lateritic type of soil. The relation between silica and sesquioxide soil is known as silica sesquioxide ratio. So let's understand how it happens. Let's take a lateritic soil. In lateritic soil, let's understand lot of rainfall happens here. This rain, what it does, here we have a silicate clay or missile which have negative charge here, and then we have cations on the outer side. This, due to high rainfall, what will happen? This will leach down. It will leach down, and then this cations which has been leached down will be taken up by your more hydrogen ions. That is called, it becomes a salicylic acid. This salicylic acid will also leach down in coming rainfall, and then left is only aluminum oxide. What is aluminum oxide? This is sesquioxide, we can say, either by iron or either by aluminum. This will be remaining as a accumulated sesquioxide. This sesquioxide, what it does? It favors aggregation of the soil. This aggregation will happen, big aggregation will happen of aluminum and ferric. So this will increase. As this will increase, it will be as a deteriorating factor, because now there will be very less cation exchange capacity, there will be very less moisture retention capacity. So this way the soil here will be very poor in conditions, and then the increase in sesquioxides result in cation exchange, less decrease in cation exchange capacity and moisture retention capacity. So the vegetation, the trees here coming is very specific, which can come here only few, like Xylea, Xylocarpa, otherwise the species here coming will be very much poor. So these are the three things to understand in the chemical property. Let's come to the biological, where we have soil microorganism. The soil microorganism influence the biological agency. So biological affecting the soil formation, microflora, bacteria, actinomycetes, fungi, algae, microflora, protozoan, worms, arthropods. These all are very important as a biological formations for the soil. Let's have a very quick revision. As we see that free living bacteria, this is very important because they fix nitrogen. Azotobacter, these are aerobic. Then Clostridium, these are anaerobic. These are free living bacteria, helpful for the soil biological properties. Then symbiotic nodule bacteria or legumes are rhizobium. These are rhizobium, you can see these are rhizobium. Okay, this is also very important. Then we have blue-green alga which fix nitrogen from the atmosphere, Anobina. This is Anobina or nostoc, we can see. Then other bacteria are Frankia, which is very important. Even in the, we can find Frankia and Casuarina also. Then we have fungus like mycorrhiza. So these all microflora and fauna are important for biological property of the soil, because they give nutrients and fix nitrogen. Among these, we have a very good friend in the forest called mycorrhiza. Myco, we can see, is a fungus, and rhiza means it is a root. So it is a fungal root. So means fungus root refers to symbiotic relationship between fungus and root. So mycorrhiza has a network of filament associated with the trees, because we are not able to give, because a forest is an extensive area. We cannot give fertilizer only in the plantations we can do, but in the natural forest, other forests, we depend on our best friend, that is called mycorrhiza. The mycorrhiza, what does mycorrhiza do? Let's understand about the mycorrhiza. What they do, they form a network with the root, and see, they have increased, this mycorrhiza has hypha which has been increased, mycelial stand, increase the area of absorption. See, they have increased the area of absorption. Roots are up to here, but mycorrhiza increase the area of absorption. They provide phosphorus, they provide zinc, they provide copper, hormone, water, nitrogen. A lot of things they give to the trees. We can see, this is a diagram, we can see a mantle. Mantle means outer side, you can see this is a covering of this mycorrhiza. Inside we can see some hearting net. Okay. HARTING, hearting net is there. It goes in the intercellular spaces, and then it doesn't harm the tree. It goes in the intercellular spaces of the root cortex, and then it provides what you say, lot of benefits like phosphorus, nitrogen, micronutrients, phytohormones and water to the tree. So this hearting net is very much important as a grows between the root cortex, and this they colonize the plant root and develop the symbiotic association called mycorrhiza. They form a network of association with the roots. This is a fruiting body are coming outside. So this is very important as a mycorrhiza. So importance of edaphic factor, let's understand the importance. What is the importance of edaphic factor? Very simple. Now the edaphic soil, it is important for the forester for the seed germination and anchoring the plants to the soil. It is very important. It gives you water, it gives you nutrient, it gives the support, okay, and germination. So these things are very important for a forester to understand the soil, and then we can manage it very nicely. Because we can manage the soil, we can understand it very nicely, because the parent material is very important. Again, I am telling you, parent material is very important, because this parent material influences the vegetation. Now some example as a examination point of view also, we can understand how the soil provides the basis for the life. Actually, soil provides the basis of life and growth. So it is the important duty as of a forester now to maintain the and improve the soil productive capacity. Then only we can have a very good vegetation. So the distribution of the tree species on the varied variety of geological formation and species competition depend on property of soil. So we have to understand as a forester. So that's why soil property, either physical, chemical, biological, we have to understand. Because now this, as I'm telling of geological formation. So let's see the geological formation. As we have laterite soil, see this is a laterite soil. We have, as I told you, laterite soil, we have very less cation exchange capacity or water holding capacity, just silica sesquioxide ratio, just I explained. So we have a species which can adapt here is Xyla xylocarpa. So as a forest you can understand what to grow there. So if we have Tectona grandis, and this they come in alluvial, they come in Deccan trap in the Andhra Pradesh, this area also it can come up nicely, where pH is 6.5 to 7.6, you can do Tectona grandis, and Tectona grandis comes, if naturally also it can come there. Then when we go to this quartzite soil, we have Pterocarpa centilenus, very good and very important tree species, we call it red sandalwood. Then when we go for Shore robusta, they like humid and they like a pH of 4.5 to 5.5. So one thing I want to tell you, one very unique thing, it may be asked in many exams also. As I have told you about the altitudinal zonation, where you find Pinus roxburghii, then you go higher, you have Cedrus Pinus valenciana, then you go Cedrus deodara, then you go more higher to Picea cimithiana, then Avis pindro, and then junipers. This is how the altitudinal zonation. But some cases, the geological formation of soil also determine the species position. Let's see one thing. As I say, this is Pinus roxburghii. In quartzite soil, in this quartzite soil, it, just because of this influence of parent rock, it sometimes comes in the higher altitudes than your deodar. It never happens that the Pinus valenciana, Pinus roxburghii, they come higher than deodar. But in some places where parent influence of parent rock, or you can say species composition changes now. As in quartzite, you can say in higher, if it is in the higher, it will come there. And if in the lower also, you can find deodar coming here, deodar coming in the old alluvium here, and Pinus valenciana coming in the higher one. This is one case in Himachal Pradesh, where Cedrus deodara occur in the lower altitude on fresh alluvium, whereas Pinus roxburghii above deodar in quartzite soil. Just because of that what? Just because of that parent material or the geological formation, you can find this one in the higher and this one deodar on the lower. This is one photograph you can see in somewhere in Parvati Valley in Kasol in Himachal Pradesh. You can find this Pinus roxburghii in higher and this deodar, and Cedrus deodara on the lower side, just because of the geological formation. This is one of the example in contrast to that altitudinal zonation. So thank you very much. We have covered the three categories. One is climatic, then physiographic and edaphic, and the locality. Now in my next lecture, I'll be covering the biotic factor. Thank you very much.